So sorry, how does it work? Yeah, this is
How does it work?
so good. Okay, good. So thanks, well, thanks a lot, Gerard, for this introduction. Literally, it's true. I'm working in this building, and the two of us have also worked together for a little while at EPFL and also overlapped at Jesta. But yeah, I really want to. I really enjoyed the day so far, and have really liked very much our discussion in this morning, and especially also just the breakout sessions with a poster or project presentations. That was just fantastic to go down to have the big picture, but also go down to real detailed projects. So thanks so much for having me, to the organizers, and particularly to Marcello, with whom I've been discussing. How long is it now? For 2-3 years about some of these issues that I'm gonna talk about. So 4 take-home messages, maybe to start with. So I'm going to argue maybe the first two are a little bit more interesting, I think, for this particular crowd. And again, sorry, I'm a neuroscientist, so I'm not at all specialized in neuroethics. So I'm sure some of the things I'm going to say are going to be very trivial for you, but I nevertheless want to present them today and also underline sort of a pragmatic issue of neurotechnology, neuroscience, and neuroethics. So it's a special case, in my opinion. It raises questions that may go beyond how human rights are defined or current ethics is defined, because some of the neuroethical challenges mediated or made possible by neurotechnology, again, maybe for you that sounds trivial, but are special because, and 2 examples I'd like to give today is self-identity, or having a basic sense of self-awareness, and also the sense of agency, where neurotechnology very much will interfere and change and modulate those important aspects, even going all the way to the self and something like psychological continuity that we've talked about in the session just before. And then something that I think Marcello and I are very interested in and have been discussing about, and that I think needs to be discussed a lot more. I think that current neuroethics has a lot of approaches, questionnaires, philosophical analysis, ethical analysis, but I think, and that's what I'm going to argue for, the main argument of this talk is that may not be enough. Maybe we need to really fuse and be more proactive of merging neuroscience and approaches from cognitive science and neuroscience with ethical questions, so to not have ethics or ethical investigation as a second thought in neuroscience experiments and neuroscience questions as a second thought in ethical applications, but really to combine these 2 fields. And that sounds maybe a bit strange, but I think it would be wonderful if that can somehow be achieved. And then, of course, we do need, there's a lot of human suffering. We've had many examples before. The numbers are huge. The money spent that needs to be spent to alleviate suffering. So we do need major advances in our technology in order to come up with better solutions and to understand the human brain. Obviously, neurotechnology is necessary as well. So neuroscience has always used technology. The first electrode that was put on a skull, but you could see that you can record brain activity. It has been used now for almost 100 years, once technology could be implanted. So what's really special today, and that's what I've marked at the bottom of this page, is really that those distinct fields, neurobiology on one side, psychology and cognitive science on the other, medicine and engineering, that they used to be in very different fields on a university campus, on different meetings. That's not the case anymore. And of course, computer science and AI massively is part of that field as well. So it's really one big field. So that makes it very difficult to actually decide what is neuroscience or what is neurotechnology. It's really one field. And in my own life, let's say in the last 20 years, one could really feel this fusion. So I think that's one of the reasons why really neurotechnology is also different, because there's so many more people in this field pushing the field forward. and also that these traditional boundaries do not exist anymore. So here are just some examples on the top left. Stephanie Lacour's work, I think she was here yesterday, building electrodes that are more brain-like, that are not rigid, metal-like elements in the brain that may harm the brain. So future electrode will be soft, will be becoming almost part of the brain. So there's really this kind of becoming part, not of a person, but really becoming part of biology is actually a very active research project. And Stephanie's work is part of this, really bordering on material sciences. And then the bottom left, just to give one picture that we're not talking like in deep brain stimulation, which are some examples I'm going to give, with 4 electrodes implanted in the brains, but we should be thinking, Gerard, you talked about 25 years, but maybe even in 10 years of thousands of electrodes maybe being implanted, and now also via AI and other systems being able to be controlled, and speech decoding. Christoph, you gave an example of fMRI, I think, based speech decoding. This is on the top right, a picture from Eddie Chung from San Francisco, who used this in real time in actually patients that are not able to verbally communicate to communicate. So this field, and then a medical example in epilepsy on the bottom right. So that field is moving quickly. So these are examples today, published today, working today, and I think this will be improving. And that's what we also need. This is one of the points I made. For science, for understanding the human brain, we're really very, very far away from understanding deeply how the human brain in particular works. I think amazing advances have been made for mouse or rodent brains, but that's really a 5 gram of a brain, or 5 to 10 grams of a brain towards a kilogram and a half, and all the human achievements in terms of culture and so forth. So we really have far ways to go and need much improved neurotechnology. Again, for medicine, I would not mention it, but just to say that for depression, anxiety, we have some therapies, but they are not curative in any form. They are based on, in the case of anxiety or depression, based on drug therapies that young individuals would have to take for an entire life. So they don't go to the cause. We don't have a curative approach. We don't have a causal understanding how these diseases emerge. And the same, by the way, etiology-wise, is the case for Parkinson's and Alzheimer's. And as we all know, for Alzheimer's disease, there is simply no therapy at the moment. Also, neurotechnology may offer advanced neurotechnologies many opportunities that we don't have for well-being, education, and creativity. But I wanted to also focus more on some of these challenges and that we have. And here's my first example, again, something that should be straightforward. One of the neurotechnologies that in these presentations I like to use, because over 200,000 patients have received neurotechnology, so-called deep brain stimulation, for which you see an example. How does this pointer work? Not like that. Okay. Do I have to point here? No. Anyway, well, this is maybe. I think I'll. Anyway, it doesn't matter. I will. No, I have long arms, but not that long. So, so you see basically, well, again, this is an audience who knows, right? So there's deep brain stimulation, and you see this electrode on the top right that is neurosurgically inserted, and it goes to that orange yellow structure, the subthalamic nucleus, and you have only 4 electrodes at the tip. There's about 3 millimeters in size, and if it's in the right spot, in patients with Parkinson's disease, and again, over 200,000, 250,000 patients have such a stimulator implanted, you can alleviate motor symptoms of Parkinson's disease. There's a lot of other non-motor symptoms in Parkinson's disease, and this DBS stimulation does not alleviate those symptoms, but it is a major success story. It's if you think about it, actually a very simple thing. You turn that system on, and a patient, one that I also saw in just last week again, and the shaking will disappear or appear. It's a striking success, and of course, many people will use this kind of neurotechnology not recording, but stimulating. And of course, many of you also know that future scenarios and what is actively being developed at the moment are so-called closed loop systems. So the same electrode system that can stimulate can also record. Again, recording from 2 electrodes only. And these closed loop systems, although it sounds easy, we should be recording and we should adapt our stimulation, because the current deep brain stimulation systems only will stimulate 24/7. The entire day, the same current is basically turned on and leads to those symptomatic improvements. However, that may not make sense if you sleep, if you're sitting rather than walking. So a smart technology should be adapted. And that's what researchers are doing now. And you see an example or 2 examples of the two pictures where brain activity is recorded and certain pathological oscillations can be recorded. And based on the presence or absence of those, then the type of stimulation, the frequency of stimulation, and where this will be done is adapted. So that's what's being used and what's being developed for motor symptoms in Parkinson's disease. But of course, Parkinson's disease or the DBS therapy comes with a certain cost. So who has access to those? How can we ascertain equal access? And I think this morning it was briefly discussed as well. There's active research projects on trying to adapt deep brain stimulation in different brain regions also for Alzheimer's disease. Can we use brain stimulation in order to improve memory? So a cognitive function in this case. Different number of patients, moving from 20 million patients to 100 million patients, and the costs are in the several hundred thousands at the moment for these kind of therapies. So if we would have a DBS for Alzheimer's disease, where do we draw the line? Is it only severe cases? Is it only those with mild to moderate cases? Or should we start early on? And of course, how is the global south, and how are other countries, how is this equal within countries, of course, but also within the world globally, where these expensive therapies do not exist, and there's also no maintenance, and there's also no specialized staff. So that was one short part on access, which in the case of Alzheimer's disease would be even more explosive than exists today on Parkinson's disease. But of course, these future neurotechnologies, if we stay with the example of memory improvements or restoration, may also lend itself very well to questions of enhancement or augmentation. So if a mild Alzheimer patient's memory can be restored, so what is the legal what are laws in place, or how do we make decisions in ethics about giving access or preventing access to people who, let's say, are 50 and want to prevent or want to improve their memory? And again, apologies if these are trivial or naive questions for you, but I think we will be having to answer them and come up with also pragmatic solutions for this, because again, there is a lot of research trying. The window into the brain is there with neurotechnologies, and research on, of course, memory improvements and cognitive enhancement is very active. So this line between enhancement and restoration, even within the clinic, where things should be easier, I think, and that's the point I'd like to make, is also not easy. Where does the clinic start, and where does the healthy person end, and where does the clinical part start? In particular, because the main trend, whether it's Alzheimer's disease or Parkinson's disease, is so-called early detection, 30 years, 20 years before Alzheimer's disease starts. And that's going to be based on statistical analysis only. So to my main point, that neurotechnology today, or neuroethics is special, is for this argument, or for the point that these kind of systems, again, if we stick to the memory system, is a very fundamental system generating sensations, but also cognitions, who we are in the first place. We can take identity or self-awareness. So brain systems, so the self is something that we study in particular in the lab, but hippocampal interventions on hippocampal mechanisms are those particular mechanisms that represent who we are, the self as experienced right now, but also the self over time, remembering the last time I was in this room, the last time I saw Marcello, or just remembering when the three of us, together with Christoph, quickly escaped to get a coffee. So those kind of continued representation of the self, trivial or not trivial, is something that is based on very particular brain mechanisms that Alzheimer researchers and preventive and restorative Alzheimer research are investigating today. So it's because of this that compared to a cardiac pacemaker or to a diabetes pump, obviously neuroscience and neurotechnology is very different. So here's one example. So this is from our own work, where certain areas, whether coded in blue or in red, are really fundamental systems to represent the self, or a bodily self, now a minimal self, as Gérard has presented. And what ongoing work in the lab is doing, how does the system that you see here on the left is interacting with memory systems? So how is the self now interacting with the self in time? And how do these very different brain regions, the ones on the left rather on the outside of the brain, whereas the hippocampus is deep in the brain, how are they interacting? And these studies here are studies in healthy individuals, in young healthy individuals. But of course, the systems that you see on the left are also brain regions that, by having implanted DBS electrodes in a Parkinson patient, will adapt and will change, particularly the one that is abbreviated PMC in blue, which is a key area of the bodily self, but which is directly connected with the subthalamic nucleus that is highly stimulated in Parkinson's disease. And then also to mention that not neuromodulation, of course, as you all know, is not only based on invasive techniques, but we have shown in the lab that using non-invasive brain stimulation to alter this hippocampal self across time a representing system can be modulated, can be up and down regulated, and that can come with consequences for spatial memory or self-related memory. My last example I want to give here, and that goes more into what maybe a version of experimental neuroethics could look like, is one part of the sense of self that we are more recently have gotten interested in. It's the sense of agency, defined as a definition by Patrick Haggard, the experience of controlling one's own actions, and through these actions cause events to occur in the outside world. So very basically, what is tested, how is agency tested in the lab? As you know, agency in the lab means an experiment in a single subject for 2 years. You're like, or I would be a person in the lab in the green shirt, would be sitting in a computer screen and would have to be doing a simple task, and how agents and repeat it over and over. So those 2 hours to have enough trials to do this. So it's far away from everyday situations, of course. But if you look in the middle, the darkish line, it basically starts when, let's say, I would push a button on this desk here, and I would see a button on the computer screen, and if there is a delay between the button press in physical space and the virtual feedback on the screen, and of course you can do this in VR, which is the example I will give you later, then your sense of agency that you are controlling the button on the screen decreases, and this is the dark line. So it's as if you walk into a dark room, you push the button, the light goes on. Yes, you feel like you're the agent of this action. However, if there's a delay, and let's say there's 10 different rooms and you walk into each room and there's more an unpredictable delay, your sense of agency decreases. It's not me causing it, must be somebody else or a smart room. So this is how very typically the sense of agency, which is of course a much larger concept, is tested. And so what we actually tested, without actually being at the time aware of Marcello's work on the idea of brain hacking, and that also in the context of brain-computer interfaces, one could test. So if instead of me with my right index finger would push a button and that leads to turn on the light in this room, somebody with a brain-computer interface could do exactly the same, right? You could decode, the individual would think about the comment, this would generate brain activity that can be detected, and via a computer that could lead to obviously to turn the light on and off. So what we did in our experiments, very much like in this agency experiment in healthy subject, is, well, although the patient, in our case, a tetraplegic patient, Ian, was generating those responses correctly, we kind of tricked his brain, or we hacked his brain, not maliciously in this case, it's experimental brain hacking if you want. And we did this in a way to understand. So what are limits that somebody with a brain-computer interface can actually do this? Maybe, so this is a collaboration with a group in the US, and I let Ali Rezai, the neurosurgeon, just briefly present this. There should be sound.
Signals that allow the external sleep to be able to move his hands. He's gone from small movement his fingers to much more sophisticated and progressive movements. For me, it's not about walking. But if I can really use my hands and be more independent, that'll change my life forever.
So yeah, very short video just to show you. So this is Ian, by the way, reminded me of just a session before. He did not want his device to be explanted, but exactly like the group has presented, there was no insurance for afterwards, and just there was no more staff to support him in this. But what we were interested in here is, can we test agency not in all of us sitting in this room, but how is agency in a patient like in an individual like Ian? And so we recorded the brain signals. We asked him to then to generate a hand opening or hand closing, but the signal we gave to him did not always correspond what actually he correctly generated. In a way, a very simple experiment in its basic form. So we were not interested in further improving, yet making it more perfect what he can do in terms of motor performance. We were interested in the step before, what happens in the conscious control of his movements, and how does this relate? Does he have a sense of agency like we have a sense of agency? And in a nutshell, that's what we could do. In addition, we could decode, without him having ever done any movement, his intention or his sense of agency and the strength of this agency to make that movement. So it's something that you can decode directly from the motor cortex. And here just some data to show you what then obviously science experiments would look like. On the top middle, you see the brain region with a little square where we recorded the activity. 100 electrodes were implanted there. And then the brain activity, first of all, we could manipulate agency. So it or modulate it in our experimental fashion, which was important. And then what you see on the right is also that neural activity in M1, which is actually a region to generate the action, also contains, I'm almost finished, also contains this purely subjective agency-related signal. So you could detect the signal without Ian ever having made any movement, just thinking about the movement. And the difference between the green and the black line is the difference between a normal sense of agency and an experimentally altered sense of agency, or hacked agency condition, if you want. Again, just the last slide, this is the same as I mentioned before. We have also set up an experiment in healthy subjects where we can do a very similar experiment non-invasively. Again, saying that not only once an electrode is implanted, but also from the outside of the brain in all of us, in a highly constrained environment, of course, not at home in a consumer tech application, but if it's highly controlled experimental scenario, this kind of experimental neuroethics, in a sense, having agency or not having agency, and seeing what this means in terms of brain activity, but also in terms of philosophy and ethics, is something that's possible in healthy subjects and in certain patient conditions, if they're willing to participate, of course. So again, my conclusions, very much like the take-home messages I had before. So we need a lot more advances in neurotechnology just to even have a chance to understand the complex human brain and the mind. For the medical application, it is the same. I've given you two examples, the sense of agency and also identity. Of course, to briefly hear why neurotechnology is special, but many of these changes of sense of agency and identity, that's actually happening today. So that's not in 5, 10, or 25 years. And then something that I personally think and have discussed with Marcello is something that's very important, we think, is that an experimental approach maybe needs to be developed really with experts from all the different fields, philosophy, law, ethicists, neuroscientists, psychologists, clinicians, engineers, of course, all need to be in the mix, I think, to carry out certain experiments that a certain group maybe decides. And I have no idea yet what a legal structure would look like, but that certain experiments needs to be done so that we can have real data and have an evidence-based way to guide or inform at least policy making. And that's it. Thank you.